Okay, this is my demo for the animation system. So I'm gonna talk about the converter, I'm gonna talk about the game engine and the changes I made. I have the PDF open just to make sure I didn't miss anything, and then I'll show the standalone executable for the converter running as well. So first, let me go through the converter code. So in order to get the hierarchy and animation data for a specific model, I had to create a number of data structs, which I did here. So I have a hierarchy node struct, which has the index for a current node, a parent index for the current node, and the name of the current node. So this would be for the bones in the data. I have an anim header data, which is a single struct that I'll use to hold the number of animations and the file prefix. So this might be something like teddy anim, just so I can know on the engine side what file to search for, or what chunk name to search for when looking for an animation to get using the eat function. I have animation data, which is for a single animation. It has the number of keyframes, the number of bones, and the name of the animation. And I have a bone data struct, which holds a translation, rotation, and scale data for a single bone object. So going into main, in order to get all of the data and to package it in main, I created a number of global variables, and I know this is a shortcoming. Global variables aren't that clean, but for the purposes of this, it works kind of well. So I have a vector of hierarchy nodes, which stores all of the hierarchy node structs for a specific model. I have a vector of animation data structs, which holds the information on each animation. This one's kind of complicated. I have a 3D vector for the bone data, and the reason I do this is because there's multiple animations. For each animation, there are multiple keyframes. For each keyframe, there are multiple bones. So I store this all in a 3D vector. And that way it stays sequential and is exactly how I expect. And then I have an anim header data, which will again store the number of anims, the name of the file prefix. So going down here, this is all standard. I'll initialize file handle, file error. I'll initialize the output. I'll use the output file name to initialize this, and then I'll also initialize the file extension. Okay, here I'll start the actual conversion process. This is display hierarchy, which will jump in here. I use extern to reference the global variables that I need, so in this case the vector of hierarchy nodes, the output file as well, because the output file will either be teddy or humanoid. I set it up to be one of those based on the input parameter name, and it'll essentially tell me to do something a little bit differently right here based on which file it is. So I have a current index, I start at 0. Here I get the root node, and then if the output file is teddy, the first relevant node that I need will be getChild0, the first child node of the root node. If it's humanoid though, there's a couple of others that are not necessary, so I'll have to call getChild 3 times to get the first relevant node to work with, and I'll call display hierarchy on that. I'll also pass in the parent index. Since the first node will be index 0, this parent index 0 doesn't matter for the first one, but it will for all the future ones. So jumping down here, I'll get the current index right here into node index, and then I'll increment current index. I'll do all of this to get the correct node name. In the case of the humanoid, I'll get rid of the humanoid string section at the beginning of the name, and then I'll replace any spaces with underscores, and I'll do the same with the parent. Down here, I'll test to make sure that Teddy Z-sphere is in one of the nodes that I'm writing to the data file, which will only be the case with the Teddy model. So this is just to ignore that. But then going down here, I'll initialize a local hierarchy node. I'll set the current index to the struct's index. I'll set the parent index. I'll copy over the current node's name, and I'll push it back onto the data vector. And then here I'll recursively do this for each one of the current nodes children, and I'll pass in the current index as the last parameter value, and this will be the parent index for the recursive call. So this will get me all the hierarchy data. Going here, I'll copy the hierarchy data into a hierarchy node array. I'll initialize the output file names. I'll write all the data to a file, and then I'll use vodka to call it and package it into an intermediate file. Moving on to the animation, I do that here in display animation. So again, I reference these external variables to get the data into. Starting here, I also start with an index channel 0. Starting here though, I get the number of animations, so in either case it'll be 3. For each animation, I'll get that current animation stack, and then I'll initialize this 2D vector specific to that animation. So this will be a vector of the keyframes, which will contain a vector of the bone data structs. So this will be per animation, and I'll push it back onto that bone data 3D vector. This animation data header will be for this specific animation, and I'll push that back onto the vector as well. And in this cur_anim data, which will be at this position right now, I'll store the name of the animation. And then again, with that output file, if it's Teddy, I'll start with the first child. If it's humanoid, I'll go a few down and start with that one. And then I'll also pass in the anim index, which will be the index value indicating which animation I'm on, and that'll be passed in here. So for the first one, it'll be 0. I'll know it's the first one. So going into display animation, I'm only going to use the first anim layer for the purposes of this. I'll get the number of frames in this animation, and I'll set the animation data header again at that anim index, so this is on the vector. I'll set the number of keyframes to that number. Here I'm looping through. For every keyframe, I'm going to get the key time. For every keyframe, I'm going to initialize a vector of bone data. So every keyframe is going to have a number of bones and the data for those bones. So then indexing into the correct spot on the 3D vector, I'm going to push this 1D vector onto that 2D vector. It's complicated and it could probably be done better, but I'm telling you it works. I'll start with index channel 0. For the first bone will be 0, and then I'll call display animation Keenan on that. And that'll take in the current anim index, which will indicate the current animation, and L count, which will indicate the current keyframe index. So, and then down here, after I'm done with all the keyframes, I'll also be done with the current animation. So I'll pass in the number, I'll write the number of bones to that animation data header in that vector at the correct spot. And I'll write and index channels after incrementing down below, it'll have the correct number of bones. Okay, jumping into display animation Keenan, that'll be over here, and you can see it has anim index and key index. Again, I'm just checking to make sure that Teddy Z-sphere isn't one of the nodes in the case of Teddy, but then I'll call display channels Keenan, again passing an anim index and key index, and this will get me the data for that current node. And then after I get that, I'll recursively call this for the rest of the children for this current node. So this will make a recursive call into every other node that I need. And I'll call display animation Keenan for that node, which will call display channels Keenan, again recursive. So going into display channels Keenan, I will get the current index, which will be index channels, and then I'll increment index channels. I'll make a local bone data struct, and then this is where if there are no curves, I'll do this. If there are curves, it'll go here. So I'll evaluate the local transform for the current node, I'll get the translation, rotation, scale data, and then I'll set that into my bone data struct here or here. And here in this case, I'll evaluate local transform based on the key time, so I'll do it for the curve. So once I get the bone data, I'm going to index into the 3D vector using the animation index, the key index, and then I'll push the bone data struct onto that vector there. So this is how I keep all of the data organized for these bones. And the same case would happen here. So this will happen recursively. It'll do it for all the bones for a keyframe. It'll come back up here. It'll do it for all the keyframes in a certain animation, and then it'll do it for all the animations, and all the data will be stored here. So going back into main, after I call this, I'll initialize a pointer of a bone data array, because this is what I'll use to actually write a batch of bone data structs into my file, and it'll be of this size. So I'll initialize the file names, I'll open the file. Oh, first here, I'll first open up a file specifically for the anim header data, so I can, when I'm opening it in the engine, I'll be able to find the anim header type and extract that specific file, so I'll know how many animations to look for after that. Here, I'll loop through for the number of animations there are, so in this case 3, and then I'll set my file names to have a specific number after the rest of the string. So in this case, let's say for Teddy, it'll be Teddy anim 0 for the first animation, Teddy anim 1 for the second one, Teddy anim 2 for the third, and this is how I'll iterate over the animations and get all of my animations on the engine side when I'm calling them using eat. So I'll open up this specific file for this animation, I'll write the animation data header first, and then I'll go through for every keyframe and I'll get the array of bone data for that keyframe, I'll copy over the data, I'll write over that array, and then I'll iterate, and after this I'll have all of the bone data for all of the keyframes for the specific animation. I'll close the file, and then call vodka on it, and I'll do this 3 times, creating 3 intermediate files, 1 for each animation. Then I'm essentially just going to call LIU, package all of them into a specific SPU package file, and that'll have all my data. So yeah, that is my converter, and so I got this executable import scene, and I have that here. So import scene and its associated DLL. I use LIU and vodka. I have my Teddy and humanoid, and I have this batch file, which I'll open up. So this is what it'll run. It'll run it twice, one for each model. So the first parameter is the program name. This is the name of the file to pass in. And then this is just another parameter I used, a string. So this will be the specific file extension for all the intermediate files created for a specific run for the program. So instead of creating a ton of .blo files, I'll create .tad or .hum. And the reason I do this is because once I'm running this batch file, if the converter is running simultaneously for 2 different models, I don't want different blow files to be packaged into SPUs for the other one accidentally, so this will make sure that it's organized and kept in the same SPU that it should be. So yeah, this will take a little bit, so I'll run this. It's running in for both, and I'll jump into the engine code in the meantime. So on the engine code side, a lot of this is the same. I initialize the camera and I set a couple of locations. This is my same camera and camera manager from last class, so I can move the camera around. This is a holdover as well. I don't know why I left that here, but then this is where it starts to get into my code. So the way I set this up is I have a scene manager singleton class that is responsible for the skeletons. I have a skeleton class which is responsible for the hierarchy and keeping a pointer to the first bone in the hierarchy, and then an animation class which is responsible for a single animation and all associated functions. But a skeleton, because in this for this assignment, each skeleton has its own animations. I made the skeleton responsible to hold the pointers to its own animations. And I'll get into that real quick. I think my converter just finished. So here is the two SPU files that are created. So I'm going to just go ahead and copy these into my game engine. So it's going to replace those two. As you can see here, I have humanoid SPU 1:42 a.m., which is right now, Teddy SPU 1:41 a.m., which is about right now. And so now when I run the game engine, it'll be using those SPU files that I got from the standalone executable. And here is where I pass in those as a parameter name. So this is where I create a new skeleton, and I do the same thing here. Just for a moment, I'll say that I have the skeleton, and what this will return is a skeleton pointer. And so I'll jump into Scene Manager's Add Skeleton. So here I will get the instance. If it doesn't exist, it'll create a static one. Since I already have the pointer being passed in, what I do is I have a linked list of skeleton pointers, but rather than giving the skeleton itself next or previous pointer, I use a skeleton node. What that is it's very basic. It just takes in a skeleton pointer as a parameter, sets the skeleton pointer variable so it holds a reference to that pointer, and then it has a reference to the next one on the list. Very simple. I do the same thing for the animations, which I'll talk about later. So going in here, I will add a skeleton. This scene manager has a skeleton node pointer to the head and a skeleton node pointer to the active. And the active is there because that'll be the one that receives any keyboard input commands. So I'll add the skeleton, create a new skeleton node, and then here is where I add it. Either if it's the first one, I'll make it the head and the active, or I'll add it to the end. Yeah, and then so that's where the skeleton is added to the scene manager. Now, the skeleton creation itself, here I'll pass in a string name and also another parameter, which I'll get to. But jumping into the skeleton class, a lot of these functions are the same. The skeleton is responsible for setting the skeleton pose, the bone pose, essentially initializing the hierarchy. And then it has a ton of other functions that I'll get into. It's responsible for the current time. The frame time just indicates like whether it's 30 frames per second or so. It has a constant value, and then delta time, the rate, the speed at which the animation for the skeleton goes. And the reason the skeleton holds all this is because I want my two skeletons on the screen to be able to have different times, different speeds, and to function independently of one another. But the animations that I'm going to get are specific to the skeleton. So that's why the skeleton also has an animation node for the head and an animation node for the current one, whichever current animation it's using. It also has a bool paused in case the animation is paused. I'll get into that. And then this is from the demos, the P first bone, a reference to the first bone in the hierarchy. So whenever the skeleton constructor is called, I'll pass in a file name. I'll also pass in an optional bone width parameter, which is defaulted to 8, but I can set it to more if anything else if I want. These variables are initialized here, and then what skeleton does is it first calls set hierarchy and then set animation. So jumping into set hierarchy down here, it'll use that same file name, Teddy SPU in this example. It'll use the eat function to go and open up that file, find the chunk of hierarchy type, and I'll get that data into eat buffer, the size of it, the chunk name as well if I need it. I'll get the number of bones by dividing the chunk size by the size of a hierarchy node, since each hierarchy node is for a specific bone. I'll initialize an array of hierarchy nodes and get all the data, and then initialize a pyramid model, shader object, graphics object, color position. Now, I'll loop through, and for every bone, I'm going to create all of the bones one by one. I'll create the game object anim. I'll set the index to the current hierarchy node array's index over here, its data. I'll get the correct hierarchy node, get its index value, get the name, so this will be for this bone, and then set the ref skeleton to this just so I know which skeleton this object is a part of. And then if data index is 0, if it's the very first object, I'll add it right to the game object manager's root. If it's anything else, I'll add it to the parent, the object which has its parent index. And I use this with the game object man find anim, which essentially goes through all the game object anims in the game object manager and finds the one with this parent index. And so I'll add it to that one. At this point, I'll have the correct hierarchy, and then I'll set the first bone to the game object anim object with index 0. So that's set hierarchy. Then it jumps into set animation. Same thing, I'm using eat, but I'm using a modified, an overloaded function of eat, which where I pass in a parameter name. That actually happens a little bit later, so I'm not going to get into that just yet. Here, I will first use the eat version that I used above, where I'll just look for the anim header type and it'll get me one back, and I know there's only one, so I can use this one. I'll get that in eat buffer. I'll set that over here, copying in the data. I'll get the number of animations, which will be 3 in this case. This is a local pointer, and then for every animation based on num anims, I'm going to, what this does is essentially uses that file prefix as well as the current index. So remember, it was teddy anim, for example, and then the index is 0. So I'm going to do this to make a single string that'll be teddy anim 0, teddy anim 1, teddy anim 2, and I'm going to pass that name in as the chunk name into my animation constructor. So before I get into the animation constructor, what I do is I create the animation, and then I add the animation to, I call this function add animation node. And what that does is let me see where this is. This is a skeleton function. I'll pass in an existing animation pointer. I'll create a new animation node, which is just a holder, and then again, I'll add it onto the skeletons list and assign it to the header current respectively. That was add animation node. Okay, so here I create the animation, I pass in the same file name, teddyspu for example, and then the chunk name teddyanim0, let's say. So I'm going to jump into the animation class and constructor. The animation class has a lot of the same stuff from the demos. Set animation data, process animation, is responsible for the list of frame buckets, has the number of bones, number of frames. It also has a paused, which I actually don't think is used, but I'm just going to ignore that for now. And then the animation the constructor takes in a file name and a chunk name, which might be 0, and this is just to be robust and in case I don't need to do it that way. But jumping into the constructor, I'll initialize this and call set animation data. Set animation data, I must have skipped it. Okay, it's right here. This is all the same pretty much from the demos. Set animation data will use eat. So if chunk name is 0, it'll call the same eat we're used to and just find the first anim type it can find. But if chunk name is not 0, I'll have a chunk name that I'm looking for. So I'll call this version of eat, which will look for this chunk name of anim type, and then I'll get that one back. Now I'll initialize an animation data struct because that'll be the first thing in this chunk, and then the following will be all the bone data. But I'll initialize the animation data, get the number of bones, number of keyframes. I'll increment the eat buffer, and then I will initialize a 2D array of bone data structs for every keyframe, and this will be of size keyframes. And then for every keyframe, I'll initialize an inner array of size num bones, and I'll copy in all the data. I will initialize the result frame bucket head, and then I'll essentially loop through the number of frames and the number of bones. So for number of frames, I'll create a new frame bucket head. I'll give it a new bone array, which will have the translation, quad, and scale data. And then for the number of bones, I will get the bone data indexing into that 2D array, and I'll copy that over, and then I'll process the animation. So yeah, okay, so that'll do that. So this creates one for however many num anims there are, and based on this file prefix, this whole thing, I'll get all 3 of the animations, and I'll add them onto the list. Okay, so I do all that. Skeleton has a bunch of methods. I'll get into that in a little bit, but this will essentially cover adding the skeletons and the respective animations. Now the next thing that essentially happens, this is set up so that this takes care of everything. It's all in the game object manager too. Okay, in the update, I'll get the input man key test, I'll update the camera if necessary, and then I'll call scene manager process animation, which will essentially just get the head skeleton node on the manager, and then loop through every skeleton node, and for that skeleton pointer associated with that skeleton node, it'll call its process animation and move on to the next one. Process animation, it'll essentially get the node's current animation and call its process animation using the skeleton node's current time. And this is that same interpolation stuff from the demos. So that's process animation. Game object man update will update all the objects. Scene manager update skeletons will go here again, loop through for every object, for every skeleton node pointer, and for every associated skeleton pointer, it'll set skeleton pose and move on to the next one. This will do all of this, and it'll set the bone pose. This is from the demos. And then update time. Because each skeleton has its own current time, I'm going to loop through all of them and update each skeleton's time using this. And so here, if I do if paused, or if not paused, then I'm going to increment the current time with delta time, and then do all of the considerations, the checking to make sure that I'm going over the max time or going under time 0, for example. But this is the key to pausing an animation and starting it back up again. Okay, I think that covered everything here, so I'm just going to go ahead and run it. So here you can see that I have my Teddy animation down here and the humanoid up here. One shortcoming or limitation I wasn't able to fix is that I wasn't able to really figure out how to move the skeletons efficiently to the right positions. So this is the best I can do. I can move the camera around so to see all of these, and then I can set it back to the starting position, and then I also have this view for the Teddy. So this one's for the Teddy, this one's for the humanoid, the ideal sort of view. Teddy is red because I implemented a quick system to make whatever the current skeleton, or the active skeleton is on the scene manager, is red. So now I'll go through some of the things that the keyboard commands that I can do. I can pause the active skeleton with the spacebar. Or first, what I can do is I can switch the active skeleton with S. So now the humanoid becomes red, the other one becomes green. I can do that. So right now the humanoid is active. I can pause the active one with space here, and the other one keeps running. If I switch it, I can pause that one too, or unpause it, switch back, unpause it. So what I can do is I can cycle through the animations for the active skeleton, the one in red, using C. So this is the punch. I can speed up or slow down using the period or comma, like the less than or greater than sign. So this is how fast it's going right now. You can see I'll speed it up once it starts again in a second. So pressing it, the greater than sign, it'll speed it up this much, and I set in like a hard max limit just so the animation doesn't bug out. I can slow it down using the other key, and this will slow it down to a minimum of 0. And I can speed it up again. I can cycle through, this is the other animation. So let's see, while that one's doing that, you can see that even as I'm increasing the speed for this one, the teddy stays exactly the same, so it's not affected. If I were to switch this one, I can speed it up as well, and you can see that the humanoid stays the same. So here, and again, I'm switching cameras using the 1 and 2 keys. That's from my engine from last class. Here I can pause this and unpause it. I can switch back. Let me switch this view. I can go in reverse as well by pressing R. So here, I'll go in reverse. Press it again, I'll go forward. Go reverse, pause it, unpause it, it's going reverse. This one will go reverse. Let me switch over here. Switch to this one, make this go in reverse. Let me switch this one's animation. Now the animation is going in reverse. Switch back here, this is still going in reverse, so maybe I'll just make that go forward. Switch that one and pause the teddy. So as you can see, all these are independent from each other. I have two skeletons appearing on the screen with multiple animations, and all these different commands while they're looping. So yeah, that's my demo. I'm gonna just make sure I covered everything, showed the converter, the standalone converter. I will upload the batch file, at least 4 animations from 2 different skeletons, so each one has 3 animations, although the 3rd animation for the teddy isn't really an animation. At least 10 animated bones. I showed the format, the structs, play, pause, forward, backwards, faster, slow, switching animations. Yeah, I think that's everything. So, some of the hardest parts, the most challenging parts I talk about in the write-up, but I think the hardest part for me was just making sure I had all the data structured correctly and was exporting correctly in the converter. A lot of my upfront work my time spent was making sure that the architecture of the system was correct and making sure that I had my classes all laid out correctly. And I started, before I even got to exporting multiple animations for a model, I went ahead and set up the whole skeleton and animations classes so that it was all ready to accept multiple animations. And I think that's why this at least works relatively smoothly, because I had the structure set up to be able to work independently and to work correctly, just simply switching to whatever thing that I need. And so yeah, I really enjoyed this project. I think this was pretty interesting, especially given that we had to take a converter and sort of rework it to fit our own purposes. And I mean, obviously, just sort of seeing something like this being somewhat of my own doing, obviously a lot of it was like given to me, but sort of just seeing this come together, at least under my own purview, sort of rewarding. So yeah, this is my animation system, and I'm looking forward to the next class. Thank you.